Hi everyone, Ross Satchell from Microchip back again. In the previous video in this series, we created an outline of a main.c file and we covered bit masks, bit positions, group masks and positions, as well as group configurations. In this video, we will create a bare metal program that toggles the onboard LED every 1 second using the built-in delay milliseconds function. So let's dive in. Start by connecting your AVR Tiny2 to your host computer and create a new bare metal project. If you have issues with the kit window not appearing, please refer to video 1 in this series. If you can't remember how to create a new bare metal project, please refer to video 2 in this series. Since we want to blink the onboard LED on our Curiosity Nano, we need to know which pin it's connected to. A great resource for the Curiosity Nano is its hardware user guide. To access it, click on the Kit window tab and it's under External Links. So let's open that and take a look at the table of contents. Looking at the introduction, it goes through the features of the board and we can see there is a user LED and a user switch. It also has an integrated programmer debugger with a virtual serial port and 2 debug GPIO channels, and features user selectable target voltage between 1.8 and 5.1 volts. Since we're looking for a pinout, let's take a look at the hardware user guide section. There we go. We can see that LED 0 is on pin PB7. It's also printed on the silk screen. Now that we know that, let's go through what we want to do. We want to set pin PB7 as an output, then we want to toggle LED 0 every 1 second. We also want to use user-readable masks as much as possible. To do that, we need the device header file. So include the device header file, hashtag or pound, include AVR/IOTN1627.h. If you're unsure where we got the header file from, please refer to video 2 in this series. To follow the header file, control and click on the include. Let's look at a struct to get an idea of what's happening. The first one is for the analog comparator, and we can see there are register 8_t data types in there. But what's that? We can control click on the data type to follow it to its definition. There we can see the type definition for a register 8_t data type is that of a volatile unsigned 8-bit integer. By making them volatile, we're telling the optimizer to not optimize any variables of this data type. Coming back to the analog comparator, if we look at the register 8_t variables, we have control A, mux control A, and status registers. If we open the datasheet to the register summary for the analog comparator peripheral, we can see those exact same variables. Then under the struct, we have 5 enums, and these are the user-readable macros. So looking at the first one for hysteresis mode, which is in control A register. So a 0 in hex is no hysteresis, a 1 is small, a 2 is medium, and 3 is large hysteresis. Coming back to the struct in the header file, we can see that hysteresis off is a 0 in hex, then small, medium, large are 1, 2, and 3 respectively. So these macros make your code much more human readable, reducing your development time as well as your debugging time. So now since we want to set up a port, let's control F in the header file to search for port_t data type. Let's also open the same section in the datasheet. The datasheet says that each port pin has a corresponding bit in the data direction and data output value registers in order to enable that pin as an output and to define the output state. Then we have the example of pin PA3 being controlled by the register direction, element 3, and out, element 3 of port A. So we can use the port B underscore macro for the direction and output registers. But what about the specific pins that we're setting? Let's search the header file for port pins. There we go. We can see the bit mask for pins 0, 1 and 2 are 1, 2 and 4 respectively, while the bit positions correspond to the bit name. For example, pin 4 is set to bit position 4. That's exactly what we need. Let's go back to MPLAB-X. So to set up the direction register, let's type port B underscore and press Control space, and we can see all of the things we can use. Let's select the direction register, and the LED is on PB7, so we can use the pin macro, type pin, then press Control space. And we can see all of the bit masks and bit positions, so we have to be careful to choose the correct one for your code. I'm going to use the bit mask for pin 7. Next, we want a while one loop so the LED blinks forever. To write to port B, we can look at the macros we have. Type port B underscore and press Control space. We have direction set, clear and toggle registers, then some output registers. That's what we want. We want to toggle LED 0 every 1 second, and there's an out toggle register. Let's use that. Now we just have to set it to our pin PB7 using the pin macros, and then use the delay function. To use delays with AVR, we need to include the delay header file and tell it the CPU frequency. Since delay is a basic utility, we can find it in the util group of headers, then add a / and we can see all of the members. We want delay.h. Next, we need to state the CPU frequency so the delay takes the right number of CPU cycles. Where do we find that? We can go to Window, Target Memory Views, Configuration Bits, which opens in the lower pane. And AVR's configuration bits can be read directly from the device before programming. Currently, all of the settings are in red, indicating that we have not yet performed a read. It is recommended to perform a read before changing any settings. Now let's click on the Read Configuration Bits green up arrow, and it starts performing a read. You'll see in the output window the application and toolpack versions, then the message Read Complete, and then the configuration bits text will now be in black as it's now the correct information. Going back through the settings, we can see frequency select, and it's set to 20 MHz. But there's likely a prescaler as well. To check, let's go to the datasheet. Section 11 is clock controller, and there's a diagram in the functional description that shows the 20 MHz oscillator as well as some other clock sources feeding into a main clock prescaler. There's a note below saying that the main clock and prescaler registers are main clock control A and main clock control B. It talks about writing to them, but we just want to read them for now. We'll come back to writing to them in a later video. Now let's go to the register summary in the datasheet and also open the header file in MPLAB-X. Control F to search, and we're looking for clock control. We can see that the registers in the datasheet are the same in the header file. Then we have a series of enums. There's clock select, crystal startup time, then there's prescaler division, which is also in main clock control B register. So the datasheet shows how various bits are configured after a reset, and the prescaler is set to 1000, which is the same as 8 in hex. That corresponds to a prescaler of 6. Now we can set up our CPU frequency. At the top of the main.c file, before the include for the delay header, we need to define the CPU frequency. So we have a 20 MHz oscillator and a prescaler of 6. That gives us 3.333333 MHz, and we can represent that as an unsigned long. Finally, we need to specify our delay time in milliseconds between toggles. I'm going to use 1000 milliseconds. Before we build the project, we need to comment out the include for the header file, as it will give an error if it's included a second time. Now we can build the project, and we can see the green Build Complete message. So let's program the device now by clicking the Make and Program Device button. After a few seconds, we can see the Programming Complete message, and the LED starts toggling every second. Congratulations, you have successfully made your first bare metal program. In the next two videos, we will look at ways to blink the onboard LED without using the blocking delay function. The first will be by polling a timer interrupt status flag, and the other will be by only using interrupts, both of which are non-blocking. See you in the next video.